Good afternoon, friends. So far, we have made an attempt to glance through wings, their aerofoil, plan form of wing, their importance. We have also talked about typical shapes of wing tips and what are their merits and demerits from designer's point of view. We talked about canard when you are talking about the aspect ratio. When you talk about aspect ratio canard, that linkage is primarily we are talking about lifting canard. There are canard which are not supposed to be predominantly for working as a lifting surface. They are like control surfaces. Their aspect ratio may not be that high. At this point, we have just glanced through those, and while coming for stability and control design, we will take each of these items precisely and see who qualifies for a particular configuration. In continuation to that, we will also quickly go through most popular tail configurations. To start with, I will not talk about various types of ingenious tails, but I will primarily talk about conventional tail and a T-tail and try to highlight what are the merits and demerits and why it has evolved like that. Any other configurations, we will be talking or discussing as and when required. When I talk about tail, when I say conventional tail, here tail, I mean horizontal tail. You understand for an aircraft, for a conventional aircraft, there is a horizontal tail, which is horizontal stabilizer, and there is a vertical tail, which is vertical stabilizer. If you see for a conventional tail, the airplane will be like this. There is a vertical tail, there is a radar, there is a horizontal tail, there is an elevator, and there is a wing, and maybe engine here. And if I see the front view, it will be something like this. This is typically a conventional tail. You will find among the youth, or also you can see in the design evolution, the stylish tail is T-tail. That is typically, if this is my empennage, and there is a vertical tail, this horizontal tail will be housed here. So it gives from the front, if I see from here, if I see, I will see this is the vertical tail, and over that, this is the horizontal tail. You are all familiar with this, right? First of all, let us ask ourselves a question. Why do you need horizontal tail? And once you know why do you need, the next question is how much we need. Who decides? The first question I am addressing first, why do you need a horizontal tail? Why horizontal tail? If you revise your stability and control lecture, you will immediately be able to answer. If this is my fuselage, if this is the wing, let's say this is somewhere is CG, or let me say this is aerodynamic center, somewhere it is CG, and this is horizontal tail, this is vertical tail. Horizontal tail will be required primarily for static stability in longitudinal plane. And also we know that horizontal tail is extremely important for a conventional airplane because it has to house elevator. In fact, part of the horizontal tail or whole horizontal tail could be an elevator which is required to pitch the aircraft up and down, right? If I put this elevator up, then the aircraft will rotate about center of gravity, and in this direction you call pitch up. So one is static stability, and when I talk about static stability, if you recall that pitching moment Cm versus alpha, the variation for small angle of attack is like that, where this point where Cm equal to 0 is the trim point. You want to fly at this alpha. That means at a given altitude, moving at a particular speed, you have decided on alpha so that the enough lift is generated to balance the weight. And why do you say static stability? Because if for some reason alpha changes, then it automatically generates negative moment which tries to take airplane to trim alpha. Who generates this negative moment? The primary responsibility is from horizontal tail. Whatever additional angle of attack changes, the lift force is generated here, and that gives you nose down moment as dictated here. So horizontal tail is extremely important from the static stability point of view, and also it has to house elevator. This is horizontal tail. Part of it can go down, can go up, and it acts as an elevator. And the elevator effectiveness depends upon the ratio between elevator area and or the tail area ST and elevator area. Right. Of course, there are planes which doesn't have tail, like typically flying wing. For a flying wing, if you want to fly, you need to have ensured that it has a reflex aerofoil so that this gentleman is positive, as well as aerodynamic center of the flying wing is behind center of gravity. So I am not digressing towards flying wing, but I am talking about conventional aircraft. So coming back to conventional aircraft, you see that if I want to fly at this trim, I need to ensure not only the slope is negative to the magnitude I designed, but also this Cm at alpha equal to 0 should be greater than 0. And to be honest, it should have a definite value for a given slope to have a trim at this alpha. So Cm naught has to be positive, and to ensure that Cm naught is positive, we heavily depend upon horizontal tail, and you know that if this is the horizontal tail, we try to give a setting angle to the horizontal tail, IT, which is negative, maybe order of 2 to 4 degrees, the typical numbers, right? This is done to ensure that even if alpha equal to 0, it generates a force here, and CG suppose is here, it gives you a Cm at alpha equal to 0 or Cm naught greater than 0. So depending upon whatever Cm naught you require, you can set the setting angle. You also know that when you are talking about Cm naught here, Cm naught can come from Cm naught tail primarily, Cm naught wing, and very small Cm naught fuselage. So message is maximum Cm naught comes from tail setting angle, You can also get Cm naught positive from the wing if I have a cambered aerofoil wing. What I do, if this is the CG of the airplane, I ensure that AC of the wing is ahead of CG. Since it is a cambered aerofoil, so there will be some negative moment Cm AC wing. So I want Cm naught wing to be positive. We see at alpha equal to 0, because cambered aerofoil, so there will be CL naught, which will act here, and CL naught into this distance the CG and the AC of the wing, let's say x bar, non-dimensionalized with minatomic chord. So this will give me additional Cm naught, which comes through wing. So message is, if you only use tail setting angle to get Cm naught desired, and the tail setting angle becomes very large, it is always advisable whenever you are using a cambered aerofoil, put the AC of the wing little ahead of CG of the airplane. So you can effectively handle the negative effect of CMAC wing through tail setting and AC of the wing location together. Right? This we know in stability control, but just to complete the discussion, I thought I'll mention this. But today, since we are focused to horizontal tail, we are more focused that tail setting angle is required, which is negative, to ensure that we get some sort of a Cm naught, which is positive. Okay? So you'll find most of the airplane is having tail setting angle negative, and in fact, you may adjust the tail setting angle depending upon what is the flight regime you are going to operate. Similarly, you have got vertical tail. And question always comes, how high the vertical tail should be. Like similar question will come here, how much tail size? And you know that we try to answer that by using a term tail volume, horizontal tail volume ratio. As long as you keep it from 0.5 to 0.8 as the initial number, you are making a good beginning. We'll come to all these things in detailed design, but I thought I'll mention it. For vertical tail also we will have some sort of a ratio, which we will discuss. Only difference is when I see VH, tail volume ratio horizontal, it is ST, area of the horizontal tail, LT, distance from the aerodynamic center of the tail to CG of the airplane, by S wing, C bar. Right? So this typical value, let's say 0.5. When I try to see the number for vertical tail volume ratio, it is S vertical, L vertical, S wing into span of the wing. So you can assume that LT and LV is the location of aerodynamic center of the vertical tail from CG. So they are almost same. S wing is anyway same. The difference is, major difference is C bar and B. B is fairly large. That is, B is C times aspect ratio, okay, for rectangular wing. So naturally, you will find the vertical tail volume ratio, as far as number is concerned, will be much less compared to tail volume ratio. It's primarily because the non-dimensionalization has been done for VV by B, not by C bar. So don't think if the number is 0.02, 0.03, we are not giving a lot of weightage to vertical fin. It's just a matter of how we have non-dimensionalized it. So this is important for a designer. Now question is, if I go on increasing this vertical fin, what are the problems? Yes, you know vertical fins are required for directional stability. It also plays important role in lateral stability. So you don't want to make an airplane highly sensitive. If we go on increasing the vertical tail, then if it becomes highly directionally stable, it becomes very sensitive to wind. Any wind, immediately it corrects. This frequency increases. You may not like it. But at the same time, what we miss generally, please understand, if I am increasing the vertical size because we are afraid, then actually I am encouraging drag due to vertical tail or vertical fin. I am encouraging it to become more and more, and the CG will be somewhere here. This will give a nose-up moment. So if you are having a vertical fin, unnecessarily you have put a larger size. As you try to accelerate, you may have a pitch-up tendencies. So that also need to be careful when you are going to do the finer design, finer evaluation. Right? So at this stage, this thing should be clear in your mind. Another part also you should see when you talk about vertical tail. The vertical tail has an end plate effect. That is, it's not like a horizontal tail where both the span extremities are open to atmosphere. So generally, if you read books and all, you do not know how much should I take the initial number for the vertical fin or vertical tail span. Roughly, if you take 1.3 times the horizontal tail, one of the horizontal tail, right? For example, if you have horizontal tail like this, you take this area, multiply by 1.3 or 1.5, and that can be good initial estimate for vertical fin. We'll talk about exactness, but this is just to give you an idea how to start thinking in terms of conceptual sketch, right? When I'm talking about vertical tail, this is the vertical tail and this is the rudder. The primary role of the rudder is for yaw control, right? Roll control, and also extremely important when the aircraft goes into stall and your aileron will not be effective, rudder then plays an important role to arrest the spin. Also you realize for a twin engine airplane, which you all know, if twin engine airplane is there and one engine is here, another engine is here, if one of the engine fails, it will immediately give yawing moment. So my rudder should be enough powerful to balance that yawing moment which is coming because of asymmetry of engine power. Most of the aircraft, twin engine aircraft, are designed primarily based on whether the rudder is sufficient or not to handle this asymmetry power, which is linked to engine failure. And also, whether rudder is enough powerful to handle the spin, right? You will find in modern airplane, there are double hinge rudders are there to increase the effectiveness. If I take the top view, so if you see the top view, you will find two locations, maybe 30%, other 50%, 55%. There are locations where rudder can be operated. So it is found that it does help to increase the rudder control power. Another way people increase rudder control power is through all movable tail. Let the whole vertical tail moves. let the whole horizontal tail moves and increase the elevator power. So if you see different evolution, you will find a lot of work was done on double hinge rudder. I strongly recommend, as I have been doing for all the lectures, please Google and see what are the airplane they have designed this, read added article, read research articles, how much percentage, how do they quantify whether it is really doing good or bad or ugly, right? Okay. So this I was touching on horizontal tail and vertical tail, keeping conventional aircraft in mind. But as I promised to start with, we'll talk about T-tail, some features of T-tail. Typically, the horizontal tail, etc., they are not cambered, they are symmetric. Okay? Now you could see, why do you want a T-tail? One of the reason for this was that at angle of attack, little bit higher angle of attack, there will be wakes. Wing wake will be there, and if the horizontal tail is in the upper side, it is likely to come into the wake of the wing, and that may reduce the effectiveness of the horizontal tail. Although it is found that if you put this at the center, it is good enough, right? But to be doubly sure at high angle of attack, which is corresponding to takeoff and landing, it is possible that you have shifted this wing from here, tail from here to here, and you are claiming that it is not coming under prop wash or wing wake. This is fine. So I am happy with T-tail, but as you go for higher angle, what will happen? The wake will go in this direction. And that time what will happen? The T-tail effectiveness will reduce. At high angle of attack, T-tail effectiveness will reduce. That means earlier whatever T-tail was generating a lift force at tail, now LT is reducing. It means now enough lift force will not be there to balance the airplane, so the airplane will try to pitch up. So for a T-tail when you are designing, please ensure that at high angle of attack, it should not generate pitch up. This is one of the serious issues with T-tail, and one has to be very careful. One should do exhaustive tunnel testing and see how the location is addressing the problem of pitch up at high angle of attack. Right? Also, you could appreciate that because now this vertical tail is also taking load of horizontal tail, so the vertical tail has to be strengthened more. So the weight penalty comes. So you are having weight penalty because now the vertical tail, which is carrying horizontal tail, all the loads, stress and all, so I have to strengthen it, so the weight will also increase. So these are the flip side. But as I told you, as a designer, you have to see how 1 + 1 gives you what result you want, right? Generally, you will see the vertical tail are thicker, for simple reason. You will find navigation radio, transducers, antenna are placed here. So it's not that it is thicker. A designer will try to use that space available. For an aircraft designer, the layout designer always look for a space. Whatever space comes, he will be say, okay, I'll accommodate this in this space. And the flight mechanics man will tell, oh, don't put it there. The CG shift will be there. So that sort of an interior designer, flight mechanics designer, aerodynamics, they quarrel. So the chief designer takes the decision in consultation. Sometimes he vetoes some aspects because he has the final goal. What are the mission requirement he has to achieve, right? Also, you might have seen the empennage, the part where all these vertical fin, etc., are housed. So there are something like this. We call it dorsal fin. These are basically strakes. These are basically, if you want to understand from the aerodynamics language, these are strakes. What are aerodynamic strakes? What is their role? Their role is to generate vortex, so that there is enhancement in the lifting capability. For example, if there is a wing, and this is a leading edge, after a certain angle, let's say this is a leading edge, and this stalls, let's say at particular angle, if I put a sharp strakes on the leading edge, then that will generate vortex which will delay the separation and also increase the lifting efficiency, right? So primary role of strakes is to do that only, to generate vortex which adds up energy to the flow, and in turn you get a efficient aerodynamics as required for the airplane. Now this is dorsal fin. This is primarily required keeping side slip in mind. Suppose the airplane, because of some reason, has gone into high side slip. Could be it has made an entry into spin and it is side slipping very fast. And the moment the side slip angle, let's say is more than 15 degrees, and there is every possibility the vertical fin may stall. If vertical fin stalls, rudder also will be ineffective. So you won't be able to control. So there this dorsal fin is purposely kept here because dorsal fin is like a strake. It generates vortex which impinges on the vertical tail and give more energy, additional energy, so the delay and effectiveness, delay is stalled and effectiveness is made more effective. So that is the primary role of dorsal fin. There are a lot of work is being done on how much should be this angle, what should be this length. This is a part of your research work, and a lot of data is also available. But for a designer, he takes the initial cue from the existing airplane, and definitely when he goes for wind tunnel testing, he tries 3-4 such dorsal fin configurations to ensure that for his aircraft, this is quite sufficient. Also, you will see ventral fins, something here. Like dorsal fin, you will also find ventral fins. They are also like strakes at high alpha beta combination. They also generate vortex which helps in improving the directional stability of an airplane. We will be talking about this in detail as we progress into design of stability and control for the airplane. But it is important at this point that you at least know, man, this is what this dorsal fin, this is ventral fin. They are basically strakes. Similarly, you will find, if you see the fuselage of airplane, right, there are strakes here also. Now you will ask me why there is a strake. See, after all, air comes from here. There is every reason to get the air decelerated, right? The energy loss will be there. So now this stress will generate vortex that will energize the falling fluid. So all these are small things, but they are calibrated in a tunnel for simple reason that fundamentally we know this is going to help, right? And from fine to finer design, this stress plays an important role. So we'll be talking about this, how to design this as we progress, okay? But at this stage, we need to know this. Just to end today's discussion, there's another important aspect for tail arrangement. When you look through spin recovery, when the aircraft goes into spin, it has stalled, it has a large vertical motion, and also it may side slip, it will spin also like this. All this combination is a characteristic of a spin. To ensure that initially when you are thinking of conceptual sketch, there are few care one can take to ensure that we have done enough at a conceptual stage to make the aircraft worthy enough to come out of spin or having enough spin recovery capabilities. And that is, if this is the empennage, and if this is the horizontal tail, and if this is the vertical tail you have designed, you could see at high angle of attack, that is why high angle of attack we are talking about, because we are talking of spin when it has gone to stall. So if I just extend it, we'll find rudder is here. So all this portion will be blanketed, they will come under the wake, and the rudder will lose its effectiveness, right? It is also possible that if this is the empennage, if you have not carefully designed the tail, and this is here, and everything comes into the wake of wing at high angle of attack. So this is a dangerous situation. Here at least some part of rudder is available. Okay. So what is done generally is, it is better that you put the rudder here, fine, and then take the horizontal tail little ahead of this. So what will happen if you take it like this? Major part of rudder will be least affected because this much will be not affected. So you have enough rudder power. What is done is, generally you draw, these are all empirical, draw around 60 degree here, around 30 degree here. This is again from Raymer. And see, by placing the location of rudder and all, how much area is getting blanketed or coming to the wake. If your 75% of the rudder is out of the wake, you should be happy. Okay? Now see, the people who volunteer for T-tail, they say simply, that if it is a typical T-tail and rudder is here, so rudder is not at all being affected because of wake, because of horizontal tail. So they advocate, oh, that is why T-tail is better. But again, for T-tail, you should know that it has an inherent tendency for a pitch up at high angle of attack. There is another campaign goes on for T-tail is, because of end plate effect, that is, this is the vertical tail, and you know end plate effect, if this is the wing, sorry, and if we put somewhere here, effectively I am making the wing two-dimensional, a step towards that, because I am not allowing flow from the bottom to come over the top, or effectively aspect ratio is increasing. We say with end plate effect means it is actually increasing the effectiveness of the wing or the fin. So by doing this, actually this horizontal tail gets advantage of end plate effect. Okay? So it becomes more efficient. So it do not require that much of size if it didn't have the end plate effect. So size reduces. Similarly, vertical tail also gets advantage of end plate effect. And in turn, you say vertical tail also becomes very effective. So I can reduce the size of the vertical tail, so there is a reduction in the weight. So what was the logic? We said because vertical tail has to take load of the wing, so it has to be strengthened. The logic is, the debate is, because of end plate effect, now they become more effective, so I can operate with a smaller size, drag reduces, and because of a lot of space here, I can use it for housing radio antennas, etc., etc. So why not I go for a T-tail? I can handle the picture. So this sort of a thing, a debate goes on, notwithstanding the comment that T-tail always look elegant, stylish. The youth, they prefer T-tail. But yes, you can use any style as long as you know whether it is affordable or not. So I think with this, I have tried to glance through the features of an airplane, wing and tail, as I look through and enrich enough to start drawing a conceptual sketch. Thank you very much.